All right, so today, Pre-Cal 20, you can put your laptops down now, guys. Thank you. Let's focus on this lesson here today. So absolute value functions, we talked about absolute value, what that is in 7.1, right? If we have a negative value and we're just concerned with the absolute value of it, then all we're concerned about is just the number itself, not necessarily the direction. So positive and negative in math and science helps us to interpret and understand direction a lot of times, positive and negative. If you have a negative change in temperature, that means the temperature is going down, getting colder. If you have a positive change in temperature, that means the temperature is getting warmer. So obviously that's important for us to know when we're trying to, interpret real life situations. But if we're just talking about what is the change in temperature, what's the change? So for example, in Saskatchewan here, what's the change in temperature that we experience in one complete year, let's say? Well, positive, negative doesn't really make sense. If you say from the middle of winter to the middle of summer, then that would be a positive change, right? We go from cold to hot. But if I'm just talking about the change, what's the variance in temperature here in Saskatchewan that we experience? Well, we routinely go from minus 40 below Celsius to almost 40 above, really. So we go from like 45 to 35 pretty typically. So what's that? That's 80 degrees variance in temperature where we live. That's pretty extreme compared to most parts of the world. A lot of parts of the world would just be, a lot less than that, depending on where you live. But anyways, so absolute value functions now are graphing these absolute values. We're not concerned really with negative values so much. We just want to graph sort of what the absolute values of the situation. So one application, you have this picture in your textbook. But this is a stroboscope picture of a bouncing ball. So it's pictures all put overlaid on top of each other. And this is a ball bouncing, right? So if I wanted to know what the total height change was, like just the overall change in height from a ball that is dropped from a certain distance, well, the ball's going to end up just like sitting motionless on the floor. So the change would be from this height to this height. But if I wanted to know how far the ball traveled in a vertical direction, in any direction, well, then I would have to measure this distance, that's this height, plus this distance, which goes up to about there, plus this distance, which goes back down to 0, plus this distance, which goes up to here, and so on, you see? So the absolute value of the ball, of the function, which this would be really important for us if I wanted to know how far did the ball travel in space. Okay, so I would have to measure down, up, down, up, down, up, down, up, down, up, right? So that's where an application of absolute value functions would come in handy. So if we have something like y equals x, that's a regular old function. An absolute value function would be y equals absolute value of x. Or if we had, a straight line, 2x plus 1, the absolute value function related to this would be, absolute value of 2x plus 1. And there would be variances as we move through math. You'll find that we have, this 2x minus 5. And the minus 5 is outside of the absolute value signs and so on. So we're going to deal mostly with just these right now, where if y equals f of x in function notation, we're dealing with, absolute value of y, which is the absolute value of the function. Okay? So this is what we're dealing with, absolute values. Let's do a quick example here. You can copy down as much of this as you want. You might just want to just watch this, but you'll have a question in your assignment just like this. So right now, I copied this from the textbook. This is a chart of x, and of course f of x we know is y, so x, y. And notice that the x and y values are identical for each point. So that's basically this line, y equals x. It's a straight line. It goes through 0, 0. And this is it right here. I'll try and draw a straight line freehand here best I can. Okay, goes on forever. All right. Now, if we were to graph g of x, which is the absolute value of y, or the absolute value of f of x here, okay, then what I would do is I would literally take the absolute value of all of the y values in these points. So for example, I look at f of x value, -3. So if I say I want to just graph the absolute value of negative 3, what does that turn into? Yeah, it turns into a positive 3, or it becomes like a positive 3. So negative 3, where's this point? Negative 3, 1, 2, 3, negative 3, right here. So the new point is actually negative 3, positive 3. It's up here. You see that? I have the same x value, and again, I'm not concerned with changing the x values, I'm concerned with changing the y values on absolute value functions. So the absolute value of negative 2 becomes positive 2, so that's that one there. The absolute value of negative 1 becomes positive 1, so that's there. Now, what's the absolute value of 0?
0.
Yeah, it still remains 0, so that's the same. What's the absolute value of 1? 1. So right there, absolute value of 2 is 2. So what you see on the positive side here, thank you, congratulations. What you see on the positive side here is the points, the y values do not change in value. But on the negative side, wherever you see a negative number, that number flips to the positive version, right? The negative gets dropped, and so it pops up. Now, again, we don't touch the x values. Some students are like, oh, I got to change the x and the y. No. You leave the x alone. The x can be negative because we're only dealing with the y values. That's all that we're flipping and changing around, okay? All right? So this ends up to be in black what the absolute value function of x looks like, this. So half of it's the same, but half of it is the negative version, okay? Now I'm going to go to Desmos here and show you some cool stuff. Okay, question back there?
Why do we use g of x to represent the absolute value?
You can use anything, h of x, g of x, k of x, w of x, doesn't matter. It's just a different function. It's just to distinguish between the different functions. Yeah.
Is there any reason to use g of x?
Nope. G of x is pretty common. H of x is another real common one. But like I say, it could be any letter. X of x is weird, so we wouldn't use x of x. But okay, pay attention, please. Ready? I'm going to do this quick, but this is going to make a lot of sense. So where was that x? Okay, so here's in Desmos here. Come on now, Desmos. Hello, wake up. Move. I command thee. Move. Okay. Let's change. Okay. Let's come back. Weird. Hello, Jello. Okay, there we go. Hello, Jello worked. Who knew? Okay, there's y equals x. You see that? That's the y equals x line. Look good? The y equals absolute value of x. Watch carefully. And there you go. It's the same over here, and it's the opposite sign. All the negative values boom, become positive value. Right? Okay, makes sense? Okay. Now, what happens if, what else do I have here? What happens if, okay, so here's y equals x and y equals absolute value of x. If I change this to y equals x, plus 5. Now this, let me just get rid of this. This line is y equals x plus 5. Hey boys, pay attention. Up here, please. Thank you. This is y equals x plus 5, right? Now the absolute value of y equals x plus 5, you do not have the v kind of like at 0 here. You have the v starting at y equals 0. So this becomes this right there. You see that? Only the negative values flip up to be positive. So as I move this around, let's see, where's b? As I move this around, you see it kind of rotates, it flips up right at 0 all the time, wherever that 0 is. Okay? All right. Okay. What about something other than, what about a parabola? Okay? A parabola. Now, all of the y values here are positive. Do you see that? They start, right now it starts at about, well, right now it starts at 5, y equals 5, and everything above 5. Okay? So if I move this down to 0, I'm good, but as I move this down, I definitely have some negative values for y. Everybody see that? This point right here has a negative value for y, and so does this point. All these points do. Okay, intercept, all these points, negative value. Now, if I took the absolute value of this whole thing, the positive values here of y would be fine. but the negative values would have to change, the negative y values. So let's light it up. Here we go, and it looks like this. Huh? Looks like that.
Looks like an egg.
Yeah. So in the positive regions, look, they're both the same. See? Both the same. Those are flipping. As it comes down, though, oh, the negative values. It's like a fish coming to eat you or something. That's what it looks like. It's like it's a fish swimming. If you're going ice fishing this weekend,
Not this weekend.
just beware for this fish right here. Ah, it's very scary. Okay? Okay. Is that big enough for you there? Yeah, okay. All right. Everybody's good? Here's another parabola, and here's another absolute value version of it. So, listening, as far as the graph goes, guys, if the entire function is in absolute values, that like x squared, like this one down here, x squared plus x minus 3, everything is in absolute value, if everything, then that means that you look at the x-axis, and it's like you fold it. It's like you fold the bottom half up over top like this, and you overlay it. So everything gets reflected up. That's if the whole thing is under the absolute value. If it's not, like let's say we have a, watch this, plus 3 is going to be outside of the absolute values. Look at that. The whole absolute value graph moved up 3 units. So if everything is in the absolute values, then you just draw a line on the x-axis, and everything that's underneath there, you flip it up. Every point flips up. Okay? And it's like you're folding a piece of paper up. Make sense?
Yep.
Question? Josh?
What would happen if you had a equals absolute value y in that equation? Would that?
The y's on the other side. So this is y equals. Y equals. These are all y equals.
If you had an absolute value y in that, what would that?
Inside here?
Yeah.
Another time. I mean, another. We'll do that another time.
I'm so curious about that.
Yeah, you can check it out on your own. We're only dealing with. I don't want to go off on a tangent or confuse anybody. So yeah, so the y is always non-absolute value equals, and then the absolute value is going to be on the other side with the x. Okay. Yes.
Could you add 5 to it?
To this again.
Yeah.
Okay. Plus 5. Whoops. R5. What? Yep.
Why is it still transition?
Why is it still like this? Because look what's in the absolute value signs. This parabola is in the absolute value, right? So without the 5, right? Without the 5 there, that's what the parabola looks like. Got it? Now, if I take all of these values that exist on the black graph there, and I move every y value up 5 units, every one, I move them all up 5 units, then what happens is this graph, here I'll just do plus b here, or plus d, I'll add a slider for d. So if I just move this up 5 units, 6 units, 7 units, 10 units, see? Everything moves up. And if I subtract a certain number from each, then this is what happens. Okay? So we're not going to be worried too much about that right now. We're just looking at the whole function is absolute value. So that kind of fold point is right at 0 there.
So then technically, if like d is negative, then values can still be negative.
Oh yeah. You can have negative values in a function that has absolute value signs, but not when they bracket everything.
Okay.
Yeah. And that's normally what we are working with here. Okay? All right, back to the notes. From your textbook again, there's a little bit of a summary. Guys, hey, come on. An absolute value function is a function that involves the absolute value of a variable. And like I say, most of the equations that we're going to be dealing with, the absolute value is over the entire equation on the kind of the right side. So it's going to be y equals absolute value of, and there might be a bunch of stuff in there. If that's the case, then there can be no negative values. Everything has to be above the x-axis. Now, I want to spend a few minutes on this because this is the tricky part of this lesson right here. It's called piecewise functions. Now, you're going to be dealing with piecewise functions from now until the end of your math career. So it's going to come up next year in Pre-Cal 30 quite a bit, and in Calculus 30 quite a bit, and forevermore. So what is a piecewise function? If you've never heard of a piecewise function before, it is a function that is split up into pieces. Okay, at its base, that's what it is. It's a function that is split up into pieces. Now, why would you split a function into pieces? You would split a function into pieces because of something like this, an absolute value. So notice that you have, for an absolute value function here, you can clearly identify a positive, sort of this section is different than this section, right? But they're somehow related. And they're related to the original graphs. So a piecewise function often expresses different parts of the domain with different kind of looking graphs. So in Pre-Cal 30, don't write this down, but in Pre-Cal 30, we are going to be able to do a graph like this. As you can tell, let's see, this is a piecewise, this f of x, this is y equals f of x here, but it's a piecewise function. So this piece is a certain relationship, this piece has another relationship, and this piece is like a parabolic relationship, you see, two lines and a parabola. And then the domain is separate. So here's the first part of the domain, here's the second part of the domain, and here's the third part of the domain. And so piecewise functions are going to be important for us to be able to graph and interpret graphs of things that are not sort of typical one expression functions. So that's what's going to come up in Pre-Cal 30 and Calculus for you. But right now, this is where we start to learn about this. So notice that what they have here is y equals, and there's like a big brace here. Okay, that's a funny bracket there is a brace. Y equals, there's two parts to this overall function, the absolute value function. It looks like x, so it looks just like y equals x when, or if, x is greater than or equal to 0. So if x is greater than or equal to 0, they're saying that this function is exactly like exactly like a regular x. Okay? So this is the y equals x line, the red one. This is the y equals absolute value, which is what we're piecing here. So the second part of it is this y graph. Yeah, if x is less than 0, then this absolute value graph of y looks like the negative version of y equals x. So it looks like the graph flipped up like this, right? The negative version of the graph if x is less than 0. So here's two pieces of this function. Okay, two pieces. Y, the absolute value of y, the blue one that we're trying to describe, looks like x if x is greater than 0. And it looks like negative x if x is less than 0. So the piecewise functions have, it looks like this in this domain, and then it looks like this in this domain. And in Pre-Cal 30 and Calculus, we'll have like maybe 2, maybe 3, maybe 4 pieces. It looks like this in this domain, it looks like this in this domain, it looks like this in this domain, and so on. But if you get the concept, this is the part where they introduce this piecewise function concept. Okay? So initial thoughts, any initial questions? Or do you have to like chew on it for a little while and just think about it for a bit? All right, we'll get a little bit more practice with this, but I know this is a strange thing for those of you guys who haven't seen this before, so I want to take a few minutes on this. All right, I just grabbed this from Desmos here. Obviously, the red is the y equals x. The black part, which would be underneath this red part here, and then bouncing up here like this, that's the absolute value part, right? So you've seen that. And the other thing I wanted to show you is that, look at this point right here, is negative 0.5, negative 3.25. Well, that point transforms to negative 0.5, positive 3.25. So every y value gets jumped up to the positive version. Should be easy. Now, do you switch the positive y value, go down to the negative? No. You don't touch that one, you leave it. So all the positive y values stay the same, all the negative y values just get changed. All right? Okay. let's do example 1 together. Maybe grab that door for us, Josh, would you mind? Thanks. Let's do example 1 together. Consider this absolute value function y equals absolute value of 2x minus 3. And this, I think this is just a random cursor that shouldn't be there. So y equals, I'll write that a little bit bigger for you in the back. Looks like that. And use these straight brackets. Don't put like these on them or anything like that. Okay, that's not absolute value. So don't do that. Just a nice straight bracket. So determine the y-intercept and the x-intercept. Okay, well, this is all based off of y equals, it's kind of like y equals 2x minus 3 without the absolute values, right? So if we found the x and y intercepts for just the regular function, we can figure out what the x and y intercepts are for this. So the y-intercept is when x equals 0. So y equals 2x minus 3. That's y equals 2 times 0 minus 3. Or y equals negative 3. So that's what it is for this graph. Is it the same for this graph, do you think? It's not actually, because this is my original black graph. This graph right here in blue, the absolute value, has to go like this, doesn't it? So if this is the y-intercept for the original black graph down here, negative 3, what's the y-intercept for this graph? Positive 3. Yes. So it's 0, positive 3. Now, what's the x-intercept for this graph? Well, that one's pretty easy. And again, you can just think about this as the regular function. But y equals 2x minus 3. Put the 0 in there. So that's 3 equals 2x. That is x equals 3 over 2. So this is 1.5 or 3 over 2 right here on the x-axis. So it's 3 over 2 comma 0. So y-intercept, x-intercept. Hi.
So if in the absolute value it was 2x plus 3,
Yep.
then that means your y-intercepts.
Yeah, the y-intercept would be, so it was 2x plus 3. The original graph without the absolute values would look like this. And then the y-intercept would be the same for both. But the x-intercept would be over here. So the blue, yeah. But the y-intercept would be the same if it's positive to begin with. And you could just put 0 in here for the absolute value. Like 2 times 0 minus 3 is negative 3. Absolute value of negative 3. Positive 3. Easy. You don't have to like go back to the original one. I just kind of wanted to show you what the original would be and then why it's the other one. Why it's the positive version. Okay, another possibly new term. I don't know. I think we've talked about this before, but maybe not. Invariant points. Have you ever heard this term before? Anybody? No, I'm seeing some head shaking. Okay. All right, well, this is very important as well. Super important. You're going to have to know what this means for the rest of your math career. Invariant. Okay, so variant means it changes. Invariant is the opposite of that, means it doesn't change. So a point that does not change between, two graphs that are related. So it's a point that remains unchanged when a transformation is applied to a graph. So between y equals x and y equals absolute value of x, right? We know that there are many invariant points, and all those invariant points come from here and go on. These are all invariant that I'm kind of highlighting there. So the ones that don't change upon a transformation. So you'll hear mention of variant and invariant points. Okay, so brief lesson here on 7.2. Let me go over the key ideas. These are in your textbook. You should be reading these at the end of every lesson to make sure that you've got everything checked off. Like, okay, I remember learning about that. I understand this. Oh, I have a question about this. Okay, so you should be taking a look at these after every lesson. So you can analyze both absolute value functions in several ways. Graphically, by sketching the original graph and then flipping all the negative values up. That makes sense. Algebraically, by writing a piecewise function. So we just kind of introduced that. It might take some time. In general, you can express y equals absolute value of f of x this way. Y equals regular old f of x when x is 0. When x is greater than 0. Oh, okay, this is a little bit different way. So the absolute value of this function means that if the function is above the x-axis, that means that it's positive, then it looks just the same because the f of x is positive. If the f of x is negative, then you have to flip the graph. So this notation's a bit confusing, I would say, for you guys that are just learning this. But it's basically saying that if you have a graph that looks like this, the absolute value graph is the same when the graph is above 0. So it's the same when the graph is above 0. But it's the opposite, or the negative version of it, when the graph is below 0 there. Okay? It's basically this that we took a look at. All right, for, I don't know what day this would be. You guys can start this. This would be the first half, so for whatever tomorrow is. What's tomorrow, Wednesday? This is gonna be Wednesday. So I'd like you to start the first half of this assignment. You have about 7 or 8 minutes of class time left, so go ahead and get started on these questions here. Do a little bit for homework tonight, and I'll give you a little bit of time to finish the rest of this.
Okay.
Sound good?
Yeah.
You can make it quick, yeah.